Greetings, detectives. Mrs. McKay here, and we are going to work on the very last learning target clue, which is clue 5.5, combining functions. So let's start by going ahead and writing our learning target clue, finishing it out. I can combine functions. This should be fairly simple. But before we move on and actually work on this, I want to do a little bit of function review because I still notice that some of you are struggling with function notation. So when you see f of x, always remember that does not mean f times x. This means the function of x. The function of x. And if you go back and remember to very early on in our year, we talked about having a function machine. Okay? So our function machine, we put something in, something happens, okay? We'll say function f of x, and we get an output, okay? We get an output. It spits something out. The function is what happens to the input. So something goes in, we do something to it, and it spits out an output, all right? This is called an independent variable. Because we can put whatever we want in, okay? And this is called the dependent variable because it is dependent on the variable that we put in and what happens to it, all right? So this is typically our x, and this is typically our y, all right? So we put x in, something happens to it, we get a y out, all right? Now, when you see f of x, if we said f of x equals, basically that's just the rule, the thing that we're going to do. So whatever x is, we're going to do something to it. So we could say x, we'll say 4x plus 3. So every time we put an x in, if we put 1 in, we put it in place of the x. We'd say 4 times 1 is 4 plus 3, out comes 7. So let me show you what I'm going to do here. Okay, so we put 1 in and we got a 7. So that was finding out f of 1. F of 1 equals 7. Let's try putting in a 2. If we put 2 in, f of 2, we find the function of 2, then that means we put 2 in our machine, we multiply it by 4, that's 8, plus 3 is 11. All right, so f of 2 is 11. If we put in, let's try negative 3, all right? If we find f of negative 3, we put 3 into our machine, negative 3 into our machine. Negative 3 times 4 is negative 12, plus 3 is a negative 9. Okay? Input, output. This f of x is just representing the rule that we do, the function that we do to the x, to the independent variable, to get the dependent variable y. All right? So, so just always know that when you have f of x, and it doesn't have to be f of x, it could be g of x, it could be d of x, it could be q of x, it could be, you can have a different variable. The important thing is that it's a function that represents a rule, and this is the rule right there for this particular function, this linear function, okay? So if I could write this as an equation, I would write it as y equals 4x plus 3. Or I might say the function of x is equal to 4x plus 3. And all that means is whenever I put something in for x, I'm going to do 4 times it plus 3, and I'm going to get an output. Okay? All right, now let's talk about this little problem that I have here. Allie and Dane. Allie and Dane work at a water park and have to drain the water at the end of each month for the ride they supervise. Each uses a pump to remove the water from the small pool at the bottom of their ride. The graph below represents the amount of water in Allie's pool, A of x, okay? And Dane's pool, D of x, over time. So we have two different graphs, A of x and D of x. A of x represents the amount of water in Allie's pool over time as it's draining, and Dane's pool, D of x, represents the amount of water in Dane's pool over time as it's draining. Okay? In this scenario, they decided to work together to drain their pools, that should say and, created the equation G of x equals A of x plus D of x. So they want to work together using their two pumps and see how much time it takes to, to be able to drain both sets of pools. So using the graph below, showing A of x and D of x, create a new set of axes and a graph G of x, and identify G of x and label it. All right, well, before we start doing any combining, we need to really understand what's happening here. So let's take a look at our graph. A of x is in blue, D of x is in orange, and we need to be able to understand what this is saying. So here is where Allie's pool is at the beginning of this is the amount of water in the pool. Here it is at the beginning when she hasn't drained anything. And then she starts draining water, and it's going down at a consistent rate, so a constant rate of change. And this is when it's empty. This is the amount of time it's passing in minutes. Okay? And then this is Dane's pool. Dane, his is the kind of orange color. This is the amount of water in his pool, and it's draining at a constant rate, and it takes this many minutes. All right? So before we go any further, I'd like you to make some observations. Make some observations. Maybe you can tell me whether these lines are increasing or decreasing. Maybe you can tell me which pool has more water in it, or which pool takes the longest to drain. So see if you can answer, just kind of maybe write 2 or 3 observations for me. Write a few observations for me. Write them down and then also record them on the Educannon. So I noticed a few things. I noticed that Allie's pool has more water than Dane's pool. I also noticed that they're both decreasing. So the pump is working at a consistent rate and the water is going down, the water level is going down until they meet 0. There's no more water in the ride or in the pool. I noticed that Allie's pool, even though she has more water in her pool, she actually empties her pool faster than Dane does. Dane's pool takes longer to empty, even though it has less water. When I look at it, I can just tell from the steepness of these lines that Allie's pool must be draining at a faster rate. Okay, I can also even identify the domain if I want, but I can't quite yet because I don't know what all of these hashtags mean. So we're going to now try to write some equations for these lines. Let's see if we can write an equation for the line, shall we? And I'm going to help us by giving us a little bit of information. Up here where it says Dane figured out that the pump he uses drains water at a rate of 1,000 gallons per minute, and it takes 24 minutes to drain. Okay, so his pool drains at 1,000 gallons per minute, and it took him 24 minutes to drain. So that means that the slope of Dane's line, d of x, is going to be 1,000 gallons per minute, okay? And I know that my minute, because if I look at my graph up here, this says amount of water in thousands, okay? So that's in essence going to be my y, right? And then down here, my graph says that this is the time in minutes. So I know that my x value is going to be the minutes. So 1,000 times 1 would mean that in 1 minute, he has that his pool has drained 1 minute. In 2 minutes, it will have drained 2,000. So the question is, how much water is in Dane's pool? Because we know that it took 24 minutes to drain. Well, I can figure that out by replacing at 24 minutes, Dane's pool will have drained 24,000 gallons, and then it will be empty. It will be totally empty. So that must mean that where he started is 24,000. So I'm just going to write 24,000 right here. Okay, I'm just going to write 24 because it's the water in thousands. Okay, so 24 right there. And I know that it took 24 minutes, so that means it was at 0, right? I'm sorry, 24 is right here. Not at Allie's, but at Dane's, d of x, right? He started at 24. So this right here is 24. And we know that it took 24 minutes. So this is 24 minutes. Okay? 24 minutes, and it is draining, and he started at 24,000 gallons. Now that we know a little bit about Dane's pool and information, we can actually write an equation for Dane. We can say that d of x is equal to 1,000x, which is how fast his, the 1,000 is the slope, 1,000 over 1, 1,000 gallons per minute, times the time, which is x. And then I'm going to actually say this is a negative 1,000 because it's removing water. So it's a negative 1,000x plus the y-intercept, which we now know is 24, or 24,000. So I've just written an equation for this line. And let's just double check it. Let's see if it's really the case. Let's look at a point. What's this point right there? Because that looks like it's right on the line, right? So this would be 1 minute, 2 minutes. So 2 minutes, and how much has drained? Well, we need to actually figure out what these markers are, don't we? And it looks like I have a 4 here, and it looks like every hashtag or every 2 marks on my graph is 4,000. So let's see if that works. 4,000, 8,000, 12,000, 16,000, 20,000, 24,000. Okay, it works. So then that must mean that this is 22,000, right? So at 2 minutes, it went down from 24 to 22,000, which means in 2 minutes it went down by 2,000 gallons, which means that in 1 minute it would have been halfway, which would have been 1,000. So this slope is 2,000 over 2, another 2,000 over 2 minutes, or 1,000 over a 1, right? So the rate of change is 1,000, and it's for every minute. So 1,000 times x will be able to tell me I can pick any amount, any time, and decide. So let's see, this is 1, 2, 3, 4, 5. Let's say this is 5 right here. How much has drained from his pool in 5 minutes? Well, by looking at my graph, it looks like it's halfway between this one and this one. So this one's 20 and this one's 16, which means this one must be 18, right? And so this must be 19,000. So at 5 minutes, it's drained to 19,000. And we can check that to see if that's right. Negative 1,000 times 5 minutes is negative 5,000. 24 minus 5,000, or 24,000 minus 5,000 is 19,000. So this is working just right on this graph. So now that we know what our labels are, we can actually now figure out what A of x is as well, what A of x is. So let's go ahead and write A of x here. So we don't really know what the rate of change is, do we? We don't know what the rate of change is. We don't know how fast. We don't know how fast the actual pool is draining. We don't know it. We could actually maybe try to figure it out by picking another point, like maybe this point right here, or we could use algebra to figure it out. So we don't know what the slope is, so we're just going to say m, okay, times x, which is the number of minutes, but we do know what the y-intercept is. What's the y-intercept? Well, the y-intercept is up here, which is 28,000, isn't it? 28,000. So plus 28,000. And we know it's a negative slope. We can see that it's a negative slope because it's sliding down the hill. We also know it's negative because we're draining the pool, so the amount we're going to keep subtracting from this 28,000. So now we just have to figure out what the how long it's going to take to drain. Well, we know how long it's going to take to drain because we look down here and we can see that this is where the pool is empty. So we know how long it takes to completely drain to get to 28,000, right? Or to get to 0. And so now we just need to figure out what this is. So tell me, what is the value, how long did it take Allie's pool to drain? You should have been able to count and just see that it took 20 minutes, okay? So we know that at 20 minutes, the amount of water in the pool is 0. So I'm just going to write a little 0 here, equals negative m times 20, okay, plus 28,000. So that means how fast did it have to be draining to be emptied at 28,000, to be empty at 20 minutes? So I'm just going to go ahead and solve this. I'm going to put the 28,000 over on this side. and that's equal to negative m times 20. I'm going to divide by 20. I'll divide by 20. And I get negative 1400 equals negative m. So therefore, m equals 1400. So that means that the rate of draining, or this pump drains at 1400 gallons per minute. So now I can go back and I can rewrite my equation by putting 1400 in for m right here. Okay? So I'm going to go ahead and write a of x equals negative 1400. It actually should be x plus 28,000. Okay? Does that make sense what I just did? I hope so. So, let's go ahead and now try to combine these two. So I'm going to write those down. I'm going to write my two equations down here at the bottom. I'm going to have d of x. I'm going to put that in orange. And we now have d of x equals 1,000 x, negative 1,000 x, plus 28,000. Okay? No, plus 24, it's 24,000. Not okay. $24,000. And then I'm going to do Allie's, which is a of x. A of x equals negative 1,400 x plus 28,000. Okay, so now we have two functions. We have d of x in orange and a of x in blue. And what is being asked is, what if we use both pumps to drain both pools? Will we be able to drain? What will the new function be? Will we be able to combine the efforts and be able to perhaps drain the pools faster or not? So now we have to figure that out. So there are different ways that we can combine these functions. We can look at these two lines and we can say, well, let's see, we now have 52,000, because when I add 28,000 and 24,000, I get 52,000 gallons that are going to have to be drained. But I have two pumps. One drains at 1,000 gallons a minute. The other drains at 1,400 gallons a minute. And, and I can put them both in the same pool and drain faster and then move to the other. Or I could put them in the pool and drain one and then move the other over. I have lots of different things that I can do. But I'm going to combine the use of both of those pumps. So I have to be able to combine that rate, okay? So in essence, I'm kind of going to be thinking about my rate of, I've got 1,000 gallons and 1,400. So in essence, I'm really being able to drain 2,400 gallons a minute, right? Because I'm using two pumps at the same time. So now that I have that kind of in my mind, I could go ahead and graph this, but actually it's going to take a while because if I have to do 52,000, I'm going to have to be way up here. So I think what I'm going to do now is, instead of trying to make a new axis, is I'm just going to change my values y-axis, and ignore the ax and the dx, because now I'm going to change the scale of my y-axis so that I can fit my two on there. All right, because I don't really have room to make another one unless I make a really small one over here. So, but before I do that, well, no, I'll go ahead and do that first. Okay, so what I decided to do was I decided to make each, instead of making each mark be 4,000, I'm going to make it be 8,000. All right, so that then means that my 52,000 is going to be, so I have 8, 16, 24, 36, no, 32, that's 32, 40, 48, 56. So then this would be 52 right here. Okay, so that would be 52 right there. Okay, so that's the combination of the two, and I think that these this blue and orange is probably going to cause you some confusion. So hopefully you'll be able to not look at those, okay, because we've changed the scale. These would actually be moved down here. The a of x would be somewhere, let's see, would be somewhere down here. Let's see, a of x was at 28, so now it would be, this is 24, so it would be right here. So if I put my a of x here, okay, and maybe draw a line, we can keep the same, scale for time, but we need it to be we need it to be I just can't, my tablet's not long enough to extend it. There you go. You get the idea. All right. So there's a of x, and then let's put our orange one. Let's do orange, which would be at 24,000. So it's going to be right there. Okay. And then we will draw a line. This is going to be even harder. Try to connect the two. All right, there we go. That's the best I can do with my free hand there. So there's, and that is d of x. Okay. Oops. So now we're going to make a green one, which is g of x. And we've said that it starts at 52,000 and that our rate of change is 20, instead of 1,000 or 1,400, it's actually 2,400, right? 2,400 per minute that's draining, because we just combined our two pumps. So if we're going to go 2,400 per minute, then that means, let's see if we can get to something that will be equal to 48, or one of these 8,000. So if it's going 2,400 in 2 minutes, I'm going to write down here, 2400. 2 minutes would be 4800. Okay. And 5200. And let's see, I'm trying to at least get to, because these are 2000s, right? So 2000 and 4000, 4000, 8000, 12,000. Okay, so let's see, 20, 52, this would be 1 minute, 2 minutes, 3 minutes. So another 24 onto this would be 76. So we're kind of close. It's just going to be hard to graph it very well. But considering that I'm doing such a terrible job at graphing anyway, we can try that. All right, so let's see if we can do this. So in 1 minute, it's gone down 2400. So we're going to go, if this is 4,000 from here to here, then 2,000 is about halfway, and it's going to go a little bit further than that. So maybe right there. Okay. And then we could try to extend the line, but you can see that trying to graph it is going to be a little difficult, right? So let's try and do it using algebra. All right, let's try and combine these using algebra. So here we want to know what d of x plus a of x equals. It's going to be equal to g of x. So we're actually creating a new graph or a new equation. Well, all we have to do really is add d of x to a of x. Okay? So d of x plus a of x equals g of x is what we've just said. So let's just combine our like terms. We've got negative 1000x and negative 1400x, so that's going to be negative 2400x. So do you see what I'm doing? I'm just adding these up, just adding them together, combining like terms. I can add my x's, and then I'm going to add my values here. This is my y-intercept. 24,000 and 28,000 is 52,000. Now, if I want to know what x is, so I can find my endpoint down here, then really all I need to do is say, well, what is x when the amount is 0, right? When we get down to the bottom, because the y will be 0, g of x will be 0. When we do our function and we multiply it by the number of minutes and we add it to the 52,000, when are we going to get 0? When are we going to get 0? So in essence, what I'm saying is, when does 0 equal negative 2400x plus 52,000? Well, that's just a simple division problem. So I'm going to go ahead and say that when if I add this 2400x over to the other side, then I just have to divide by 2400. And so I'm going to pull out my calculator. And divide 5200 by 2400. So 52,000, divided by 2400 equals 21.66666666. Okay, so x equals 21.66, etc. And that just means 2/3, which it basically means 2/3 of a minute. If there are 60 seconds in a minute, it means 40 seconds. So it's between 21 and 22 minutes. So now I have an endpoint. I know it's going to take 21, but not quite 22 minutes. So 21 and 2/3 seconds. So I'm going to put it right about there. And I just have to graph that. So here I have my start up here, and I have my end down here, and then, of course, the trick is just to connect the two. Okay, so I'm going to try to make that. It's too bad that's not a little bit thicker line, but you get the idea. So what we've just done is now looking at this green. Let me see if I'll just go over it like this. Looking at this green line right here, and I'm drawing very freehand. Well, that's terrible. The tablet does not seem to want to behave. Well, you get the idea. That's awful. You're a much better drawer than I am. So this green line is the combination of these two down here. Okay, we just combined these two functions, this d of x and this a of x. So it will take 21 minutes, 21.66, so 21 minutes and 40 seconds for Allie and Dane to drain both pools, which equal 52,000 gallons, okay? And they're draining at 2,400 gallons per minute. So we've just combined these two. So that was kind of a long explanation, but I wanted you to see how we could take a problem and actually do that, actually combine the two functions. So not only being able to graph it, but also being able to do it algebraically as well, all right? So when you're going to combine functions, just things to remember, it's probably the easiest if you write out your equation. So if you have a story problem or a context, see if you can turn that context into an equation. And then if you're going to combine it with another context, turn that into an equation. And as long as they have the same x's, and in this case the x was time, so it was the same amount of time regardless, then as long as it's an f of x and a d of x and a g of x and an a of x, and it's always the x that you're putting in there, then you can just combine your like terms. You just add those two together. Or if you had to find the difference between them, you would subtract them. Either way, you're combining your like terms and then you write your new equation. And so that's what we did right here. We wrote out our two equations, d of x and a of x. We combined like terms by adding our x's together and adding our constants together, and then we had our new equation. And once we had our new equation, we were actually able to graph it again. Okay, that's all I have for combining functions. Make sure you write yourself a key idea, something that will help you to remember. I do look at those when I look at your binder. If you don't have a key idea, you only get half points on your notes. So make sure that you do write down a key idea, because this is something that you can use to study from. All right, that's all I have, and I will see you in class.